As we begin our study of the stars, it makes sense to first consider our sun, which is a star, and a very important one obviously for us. And although I know it's not the most exciting thing to see a page of statistics and parameters, nevertheless our star is so important that I want to give you some highlights that are fairly mind-blowing if you really consider them. First of all, its mass, 2 times 10 to the 30 kilograms. Well, our Earth is 6 trillion kilograms, and it's 333,000 times that. There, you got a good picture of that now? Get an intuitive feel? Probably not. It's more massive than we can comprehend. It's made of mostly hydrogen and helium, and 1.5% metals, heavy elements beyond helium. It takes light 8.32 minutes to get to us, so that's the light travel time, or it's that many light minutes of distance. Here comes the Earth, zoop, onto the screen. If you saw it, there it is, magnified in its distortion. But what it's doing is showing the relative size of Earth compared to our sun, and it's very small, but 109 of those little spheres would fit across the diameter of the sun. Over 1 million of those little Earths would fit inside. So the volume is over 1 million times that of Earth. The sun has a lot of variation in density. It's gas from the surface all the way down to the core. The outer regions of the sun are extremely rarefied. In other words, they're very thin, much less dense than the air we breathe. So the average density of the sun is 1.41 grams per cubic centimeter, so it would actually sink in water. Yes, it's gas, and it would sink in water. The core, as it progressively, as you go down into the sun, toward the core, once you get to the core, you've got a density of about 14 times that of lead, and it's still gas. So that is a huge range of densities of the gas. The temperature of the surface is 5,800 Kelvin. That would be far hotter than any oven that you've experienced in your life. But the temperature in the center is many times hotter than that, 15.5 million degrees Kelvin. So you wouldn't want to look at the center of the sun without the gas that's around the core hiding the brilliancy of that incredibly hot core. Well, it shines with a luminosity of 3.9 times 10 to the 26 watts. There again, it's an exponent and incomprehensible. I'll try and give you some analogies just as to how incredibly powerful that really is. It takes 25 to 35 days to rotate, and lest you think that maybe we're just confused, turns out that's really true. The equatorial regions take about 25 days to rotate around, while the polar regions are 35 days, so it's differential rotation. It takes 26,000 light years for light from the center of the galaxy to hit our solar system, or it's 26,000 light years distance, which is very, very far indeed. 230 million years for the sun to orbit the galaxy. And to do that, it requires a speed, well, it has a speed of 140 miles per second, and therefore it takes 230 million years. The angular diameter is about the same as the moon, right around a half a degree, or 32 arc minutes. And the spectral type, which has to do with its temperature, is a G2. And the luminosity class is 5, and we'll learn what that means later on in this unit. If we consider the composition of the sun, in this case not by mass but by number of atoms, 90% of the atoms are hydrogen. So the vast majority of the pie that shows the composition of the sun is hydrogen, and almost all the rest is helium. So there's a tiny little bit that's left. There's a little sliver here, 1.5% or so, and if you expand that into a whole another pie, you get mostly oxygen, okay, and carbon, neon, nitrogen, iron, magnesium, silicon, sulfur, all the rest of the elements in very minute quantities. So that's the composition of the sun. Now, this is an incredible reality, which is basically the distance that the sun has moved around the galaxy, I like to think of it in terms of, say, the last 10,000 years, which is reasonably, I would say, the time, including all the history of modern civilization, agriculture, cities. So say about 10,000 years that human beings have been intently gazing into the heavens. And here we are on a solar system with the sun being the star that is mostly our solar system, and it is orbiting the galaxy at 140 miles per second, which is 500,000 miles per hour, by the way. The question is, in 10,000 years, the entire time that humans have been observing the heavens, say, how far has the sun progressed in its orbit around the galaxy? Well, if you do the math, you have 220 million years for it to orbit once. And considering that 10,000 years, 10 millennia, is the interval of time we're talking about, how much has the star, our sun, moved around the circle? Well, a circle is 360 degrees, and if you take 10,000 divided by the 220 million, you get a very small number, which is the proportion of the circle, the circumference that it's gone. And if you convert that to degrees, you find out that the sun has moved about 1/50th of 1 degree, which is less than a pixel. And so in 10,000 years, at this incredible rate of 140 miles per second, you would not see the sun even move a pixel across the screen. So that is pretty amazing. Think how fast 140 miles per second is. 10,000 years of that, and we haven't even moved a pixel. So the galaxy, as you saw in the very first presentation of this course, is extremely big. Remember the solar system, a quarter in comparison to the entire United States, which is the galaxy. So there's the sun traversing the Milky Way very slowly, but it's actually done it about 16 times since the origin of the galaxy. The atmosphere of our sun has 3 basic regions. We have the photosphere at 5800 Kelvin, which is the layer that we see when we look at the sun. We're actually seeing light from the photosphere. So that's the region that you see. Above that, we have the chromosphere. Chromo, color, which is just above the photosphere. The temperature rises drastically in the upper regions of the chromosphere. And above that, we have the corona, which is extremely hot but very thin, normally invisible except during a total solar eclipse. And you see the corona here, the extremely hot but very thin gas. And let's investigate these constituents a little bit more carefully. So as I said, when you look at the sun, you're viewing the photosphere. Now, in this image, you can probably see that the amount of light and the color varies from the center on over to the edge. Can you see how the edge is darker, dimmer? Well, there's a good reason for that. The phenomenon is known as, you guessed it, limb darkening. The limb, the edge of the sun, is darkened. Now there's a good reason for that. The photosphere is about 300 miles thick. We see deep into the photosphere when we're looking at photons, the photons coming from the photosphere. And when we look directly at the center, we're seeing photons that originate deeper into the sun where it's hotter. So this might make it a little more clear. So when we look at the center, we see that depth directly in. So back here, we're looking at hotter photons. Therefore, the average color is more toward the yellow. This is a black body, and a hotter black body produces a different color. So it's more yellow there. When we look at the edges, we look toward the edge, we're seeing into the photosphere, but not, because we're looking across the edge, we're not looking as deep into the sun. So the photons that we're seeing are cooler photons, therefore dimmer and more orange or red compared to the center. So that's limb darkening. When we look at the detail of the photosphere, which again is the part that we see, if we magnify a region of this, we see this mottled appearance, and these are regions known as granules. And That's what the entire surface of the sun is covered by. There are regions of gas bubbling up via convection, like a boiling pot of water, and this is the visual effect that we get. The granules we're talking about arise from the fact that energy from the interior of the sun has to make its way out to the surface. And they do so at least toward the outer regions in the photosphere via convection. Like water boiling, the hot water bubbles up and gets to the surface, releases some energy, in this case in the form of photons, and then the cooler gas comes back down. So that's all shown here. This is a granule. And the hot gas rising gets to the surface, releases photons, cools, and comes back down. And in cooling, you know it's dimmer and darker. Well, it's kind of the same thing, but redder as well. So the color changes and the brightness changes. So the brighter region corresponds to hot gas rising, dimmer, cool gas sinking. And here is Texas, approximately in comparison to the size of these granules. We're talking about 800 miles across or so. The entire surface of the sun is modeled with several million of these granules, and they only exist for minutes, so they're constantly evolving and morphing into different ones. But at the macro level, it looks approximately the same at any given moment in time. So the next layer above the photosphere is the chromosphere. Chromo meaning color. So you see this thin ring of color that's generally only seen during a solar eclipse. But it's fairly brilliant. It has multiple colors, which means there's some significant variety in the way the gas is formed. And how thick is this region? Well, here's a silhouette of the Earth's diameter, and we see these gas plumes rising up approximately the diameter of Earth. Those gas filaments are known as spicules, and they start cooler and get warmer and warmer as they rise. This image is not visible light, it's a hydrogen alpha filter, which is basically the light given off by hydrogen. So you can see the spicules fairly well. They are formed at about 45,000 miles an hour and rise up to about the diameter of Earth. As they rise, they also rise in temperature. So that corresponds to the different colors. We have visible light, ultraviolet, and X-ray, because they're highly ionized gases as they rise up further and further. In fact, to have significant X-ray emission means you've got very hot gas at that particular height. So from the lower parts to the upper part of the chromosphere, you have a tremendous change in the temperature of the gas. The spicules last about 5 to 15 minutes each, and they don't just form everywhere, as you can kind of see, like this boundary here. The spicules are actually surrounding what's known as a supergranule, which consists of hundreds, up to almost 1,000 of the granules that we just discussed. So that's where these gas plumes exist on the sun. And last but not least, we have the corona, which is the outer layer of the atmosphere of the sun. The temperature rises rapidly from the chromosphere into the corona. That process isn't very well understood, but it has to do with magnetic energy. Nevertheless, even though the gas is super hot, literally achieving million-degree temperatures, it's very thin at the same time. So it's a very thin gas that extends sometimes multiple sun diameters, depending on how much resolution and how dim we want to consider the chromosphere being before it's not existing anymore. But it's a very thin gas that's very hot. So the only time we see this is during a solar eclipse, because the light from the photosphere will overwhelm this coronal light. The coronal light itself is equivalent to that of a full moon if you cover the photosphere of the sun. So there it is. Those are the three layers of the sun. The solar wind is a key feature of our sun. You probably all heard of the solar wind. Well, what is it? What it is charged particles. And almost 99% of those charged particles are protons and electrons. Protons are basically hydrogen atoms without the electron. So if you take the electron off the proton of a hydrogen atom, you have two charged particles. It turns out that the sun is very hot and there's a lot of magnetic energy, and if these particles have enough speed, if they're given enough energy, they can achieve the escape velocity of the sun. So the magnetic energy drives the process of giving these protons and electrons enough speed to achieve escape speed. Once they do that, they lift off from the sun, never to return. And that's happening continuously. There's variations in its intensity with different subtle processes going on. But the basic idea is protons and electrons is achieving the escape speed and blasting off from the sun. So here we are on Earth, and we are in line with that solar wind, and we have a magnetic shield around the Earth. It's a force field protecting us from the damaging effects of these charged particles, and the pressure from that wind actually modifies that shield that we have in ways that are calculable and measurable as well. Turns out there's a lot of those protons and electrons coming off the surface of the sun, about 1 million tons every second. Wow, so the sun is losing 1 million tons of charged particles every second. You might think it will disappear real quickly, but it turns out it's just a small fraction of 1% of the mass of the sun that will be disappearing over the entire 10 billion year history of the sun. So nothing to worry about. The sun is incredibly massive. So the magnetic shield of the Earth is modified by this pressure from the solar wind. Well, the solar wind, even though it's 99% protons and electrons, it also consists of larger particles like helium nuclei and larger particles yet. In fact, there's reason to believe that the constituents of the constituency particle composition of the sun is similar to the original solar nebula from which the solar system came. So there was a mission sent out called the Genesis mission to try and capture some of those particles emanating from the sun. So the satellite, the spacecraft, was sent out there. The little collector collected these particles from the solar wind particles. And on the way back in, the little craft was supposed to launch, unveil a parachute and be snatched out of the sky by helicopters. Unfortunately, the parachute didn't open, so here is that poor little craft that slammed into the Earth at about 200 miles an hour. Nevertheless, there was still useful data in the gel material that originally caught the particles. So the point being that it's really useful to recognize that the solar wind holds deep and significant clues about the constituency of the original protosolar nebula that produced our solar system.